look at using the derivative to find high and low points, maxima and minima, on a function. But before we do, I want to point out something about limits. Some limits just don't exist. So, for example, I have this function. It's f of x equals x over 2 plus the square root of x over x. If you look at it, its graph looks like this. So it's got a jump right here at 0. So you can tell that it's not defined at 0 because that would have a 0 over 0. So that's indeterminate. So it doesn't. The function certainly doesn't have a value at 0, but we could still ask what's the limit as x tends to 0 of the function, and we can see what this should mean is that as x gets close to 0, the outputs should get close to some particular number. But you can see on this function that as x gets close to 0, the outputs, if you come down to 0 with the inputs, then the outputs are getting closer and closer to what looks like about 1. On the other hand, if you come closer to 0 from the left, it looks like the outputs are getting closer and closer to -1 there in those limits. So we can say that the limit as x tends to 0 from above, so I'll say x is getting close to 0, and I'll put a little plus sign to indicate that x is always 0 plus a bit. That limit looks like it's 1. So we'd say the right-hand limit is 1, but as x gets closer to 0, always a little bit less than 0, so I'll say x approaches 0 from the left, put a little minus sign after. That one looks like it's -1. So we can't reliably say that just because you're close to 0, the output will be close to 1, because there are sometimes when you're close to 0 and the output's close to -1. And we couldn't say that the limit was -1 either, because you can be very close to 0 and not be anywhere near -1. You could be up here by 1. So no limit. This brings up an important point about limits. The limit is going to exist if and only if the left and right hand limits exist and agree. So in order for the limit as x tends to c of f of x to be equal to L, you're going to have the left hand limit, so the limit as you come to c from the low side, that would have to equal L, and so would the limit as x tends to c from above. So whether you approach c from the high side of c, x is always c plus a bit, or as you make the input close to c from the low side of c, x is always c minus a bit, those two limits have to exist. They both have, and they have to agree on the same number L. So if that happens, then you know the limit exists, right? Or if the limit exists, both of these would have to be true. So we could put maybe a double-headed arrow here. If you have one, then you have the other. So, okay, and it goes both ways, which isn't always the case with implications. Okay, so we could apply that even if it wasn't a picture we were looking at, if it was actually a function. This function's a piecewise function. You can see that the function is a little bit iffy at -2. So it's hard to say what's going on because as x gets closer to -2, it hands off control from this linear function to this quadratic function. And we might ask, what is the limit as x tends to -2? Well, since the function behaves so differently on different sides of -2, one way to figure out the limit, if the limit exists, is to examine the limit from both sides. What if x approaches -2 from the low side? Well, if x is always -2 minus a bit, then this is the function 2x minus 3 that applies. So we're really asking, as x approaches -2 from the low side, what does 2x minus 3 get close to? Well, 2 times -2 would be -4. So if x is really close to -2, this would be -4 minus 3. That would be -7. On the other hand, we could ask about the limit as x approaches -2 from the high side. So x is getting closer and closer to -2, but always -2 plus a bit, f of x. In this case, if x is always a little more than -2, then this is the function that applies, right? So if you're talking about f of x on that side of -2, you're really talking about this function, x squared minus 11. Now that we've broken it down to this specific piece, we can say, okay, well, if x is getting closer and closer to -2, x squared will get closer and closer to 4. Closer and closer to 4 minus 11 is going to get closer and closer to -7. Now see, both limits, both the left-hand limit and the right-hand limit, they both exist, and they agree that the values should be -7. And so by this principle, we can say that the limit is -7. We figured that out. Okay, so can be handy to think about that. The limit from either side has to agree in order for the limit in order for the full limit to exist. The limits on either side have to agree. Okay, here's another example of a limit that doesn't exist. It's a little bit different. It doesn't just have a jump in it. Basically, we have sine, and instead of taking sine of x, we're taking sine of 1 over x. You know, sine of x, as x gets larger and larger, sine would just continue to oscillate, right, at this regular 2 pi periodic rate. But what's happening when we do 1 over x takes all of those big numbers and packs them, all the big numbers out here beyond 1, they all become less than 1. So it's going to take all these values and pack them in there. That means that all of these oscillations, those infinitely many waves rolling out there, are going to get packed into this center piece. So everything's fine, except as you approach 0. So when you approach 0, a tiny change in x is going to make a huge difference in the input, and so the function is going to start oscillating faster and faster and faster. You can see it. Here's a peak, and then the next peak comes sooner and sooner and sooner. And my graphing program is actually having a little bit of trouble because it's just plotting points and connecting the dots, and it's gotten a little bit confused, but it's still just oscillating super rapidly. It's almost like it's going so fast it fills this in kind of solid. In this case, the limit doesn't exist. If we ask what happens as x tends to 0, obviously the function is not defined at 0, but we could say, do we get close, as the input gets close to 0, does the output, sine 1 over x, get closer and closer to some value? And you can see that there's no single value, there's not even a few values, right? You keep moving back and forth here, so we don't have a limit. Just bring that up because there are lots of weird ways in which the limit may fail. We don't have a right-hand limit or a left-hand limit, and so they don't even exist, let alone agree in this case. Lots of weird ways how limits could fail, and this is just an interesting example. Well, I bring that up because derivatives are limits. And since derivatives are limits, the limit may not exist, in which case you don't have a derivative. Remember, if we wanted to find the derivative of a function at some point, we would take the limit as x tends to h. Let's see, if we want to find the derivative at c, we'd take f of c plus h and subtract f of c all over h, right? So since this is a limit and not all limits exist, the derivative may not exist. So when a derivative does exist, we say the function is differentiable. First, we talk about differentiability at a point. So if f prime of c exists, since the derivative is a limit, right? It's the limit of the slopes of the secants that gives us the instantaneous slope of the tangent, or the instantaneous rate of change. If that limit exists, so if you can find a number for the tangent, then we say that f is differentiable at that point. So f is differentiable at c. If we say it's just differentiable, then we mean it's differentiable at every point in the region where we're interested, right? So f is differentiable if it is differentiable at every point. So the derivative is a limit. That limit might exist at some points and might not exist at other points, at other values of c, right? This limit may not work out. But if it works out at every single point, we say it's differentiable. We can also talk about being differentiable on an interval. That would mean that it's differentiable at every point in a particular interval. Okay, so differentiable at a point then leads to differentiable. Now, let me show you some examples of when that derivative may not work. And one case is when you have a corner. So here's a function. It's an absolute value function that I shifted around a little bit. Everywhere here, definitely it's differentiable on all these points. So because you can see the slope over here looks like the derivative at all of these points is equal to 1. So it has a slope of 1 all over here. So for every x less than 2, then the derivative definitely exists. So it's differentiable on all of these points over here. It's also differentiable on all of these points over here, right? Over here it looks like the derivative is equal to -1 if x is greater than 2. But this function is not differentiable at 0. So f is not differentiable at 0, or not 0. Let's see, what's this point? 2 is not differentiable at 2. because the derivative doesn't exist here. You can think one reason the derivative doesn't exist is in order to find the derivative, we found a slope of the secant. So we would take some value h and we'd go forward a little bit, perhaps if h was positive, and find the slope of the secant, which will obviously turn out to be -1. Then as we take the limit as h tends to 0 from above, so we're bringing h back to 0 this way, then of our difference quotient, which would be f of 2 plus h minus f of 2 all over h, you can see that's always equal to -1 no matter what the value of h, and so definitely the derivative is -1 over there. But for the limit to exist, it has to exist as h approaches 0 in both directions. So if we make h approach 0 from the low side, in other words, if h is a negative number, then we're over here at this negative value. So we're over here and finding slopes of these secants. And if we're finding slopes of those secants, those all turn out to be +1. So this is 1 always. So as h goes to 0 from below, we get 1. Well, the two limits, the right-hand limit and the left-hand limit, don't exist, so the derivative can't exist. That's going to happen anytime you have a corner point like this, where the slope just sort of abruptly changes. That's going to create a corner point. A related problem occurs when you have what's called a cusp. Here's an example of a cusp. I did something, it was I shifted x to the 2/3 here, and it created this cusp. So what's actually happening here is as you find slopes of secants starting from this point and going out to the right, the slopes of the secants, as you bring them back, these slopes tip to positive infinity, right? They're always positive, and as I bring these back, they just get steeper and steeper. But if I were to use a negative h, or find the limit in that derivative as h comes up to 0 from below, these slopes are all negative, and they're going to tip to negative infinity. So when you have a cusp like that, where it comes down not just to a corner, but actually it's going vertical at this cusp, there's not going to be a derivative if there's a cusp in the graph. Another problem that can go wrong is if you have a vertical tangent. So this is the graph of the cube root of x. And you know that's the inverse of x cubed, and x cubed, its derivative is 3x squared. So at 0, x cubed has a slope of 0. That means that its inverse has a slope that's essentially infinite. Whether I start at 0 and move and take go out h this way and find those slopes, those are tipping to infinity, right? Even if I go backwards, I still have positive slopes that become more and more positive. So it's like the slope is going to infinity. Well, infinity is not a number, so we wouldn't say it has a derivative at that point. It does have a vertical tangent, though, right? It's like this tangent line is vertical at that point. No derivative in that situation. Another situation is when you have a discontinuity. So back to this function. Before we had it undefined at 0. This was what, x over 2 plus the absolute value of x over x. And we looked at it, it wasn't defined at 0. So I went ahead and said, well, let's just define it to be maybe -1 at 0. I just made a choice here. If I try to find the slopes of the secants, if I use a positive h, you can see that because of the discontinuity, as I make h, so I'm starting with h that's greater than 0, I'm making h go to 0 from above, that the slopes of the secants are going to tip up to infinity here, right? Whereas on the other side, if I have an h that's negative, so h is negative, and that means I'm moving backward, and I find the slope of the secant, I'm just going to find just some sort of regular slope, right? I think in this case it was 1/2 that I had. So the slope is going to be 1/2 over here. And so the two limits don't exist. The limit as h tends to 0 from above of our difference quotient, f of 0 plus h minus f of 0 all over h, that looks like that's tipping up to positive infinity. And yet the limit as h tends to 0 from below of f of 0 plus h minus f of 0 over h is just going to equal to some other number, 1/2. So the derivative is a limit, and for the limit to exist, both limits, the left and the right hand limits, both have to exist and agree, and that's just not happening here. Okay, so we're going to talk more in the next video about relationships between a function being having a derivative and being continuous and finding max and minimum points.